So we've covered most of the basic theory for how to read and interpret phase diagrams. So now let's look at some examples of real phase diagrams. So this is an example of potassium chloride, sodium chloride. Now, I'm covering up the bottom half because I want to have a bit of a reveal. This starts out with temperature versus composition, and this looks a lot like an isomorphic component. And after all, sodium chloride, potassium chloride, they have the same crystal structure, and they have very similar ionic size. So you do have basically an isomorphic phase diagram. That you do have kind of a weirdness here, in as much as, here is pure sodium chloride, here's pure potassium chloride. I think it's potassium, right? Yeah, potassium chloride. And you got melting. Here you have liquid, solid solution. Below, you have a rock salt solid solution. The crystal structures of these are rock salt crystal structure. And here you have a liquid plus rock salt, liquid plus rock salt. This is a congruent point. So what's actually happened here is you've got this isomorphic phase diagram, but now these have come in and they've pinched. So you have something that looks like so here, liquid, alpha, alpha plus liquid, alpha plus liquid. So if you have a composition, which is right at this point, as you cool down, you'll go from liquid to pure solid. And this is a congruent point, and it comes about for a variety of thermodynamic reasons, but these are not uncommon in phase diagrams. Now, something that's also interesting about the potassium chloride, sodium chloride, is that as we cool down, we have this thing that forms. So this is called a Spinola decomposition or a miscibility gap. So basically, above this temperature, which is 505 degrees C, we have a single rock salt solid solution phase, which is a mixture of sodium and potassium chloride. As you cool down, we get two actually slightly different compositions. So let me start by saying, like, let's say we start over here. Well, heat it up, cool down, liquid. Here we form liquid plus the rock salt structure. Keep cooling. Now we have rock salt structure. We keep cooling, rock salt, rock salt, rock salt, rock salt, rock salt. Now here we start to nucleate a second phase. This rock salt structure we're going to call, let's call it RS1. This side we have RS2. In between we have RS1 and RS2. Basically, this is a rock salt structure that is potassium rich. This is a rock salt structure that is sodium rich. Once you cross into this miscibility gap, you have a Spinola decomposition. So above, you just have all, say, rock salt. Below, however, you're actually going to get a solid diffusion, or diffusion in the solid, and you're going to wind up with regions that look like this of RS1 and then RS2 in these two. And this decomposition leads to, I guess, a segregation of sodium and chlorine. And above this temperature, it's all solid state. But when you pass below into this dome, you get decomposition. So this is a phase diagram that looks a lot like something you've seen, but it's actually a little more complicated than that. The rules for reading this are still the same, right? So, for example, if you're here, let's say if you're slightly above the dome, right? Well, then you still know that you're rock salt. So there's one phase, and you know the composition. If you pass below, now you have to draw a tie line. The tie line will tell you the relative phase fraction of rock salt 2 by taking that divided by that, and the phase fraction of rock salt 1 by taking this divided by this. Remember, rock salt 1's on the left side. And then you can determine the composition of rock salt 1 by dropping a line here, and the composition of rock salt 2 by dropping a line here. An interesting thing is that all materials, as they go toward 0 degrees Kelvin, and this isn't Kelvin, this is in degrees Celsius, make sure that you check the units in all of your phase diagrams. But as you head towards 0 Kelvin, entropy has to go towards 0. This is a consequence of the third law of thermodynamics, and because of that, you always get the segregation. So even when you have a happy-looking eutectic phase diagram, example, like yes, a phase diagram that does this, a eutectic. Well, what's going to happen is as you go to t equals 0, this is going to go to here, and this is going to go to here. So essentially, you wind up with, most phase diagrams don't go all the way to 0 Kelvin. In fact, if you look at the units, they always stop short, and that's because at low temperatures you wind up with these type of spinodal decompositions. But if you do extrapolate down to 0, you wind up with alpha plus beta. So this is our alpha, beta, liquid, alpha plus liquid, beta plus liquid. And then down here, you wind up with, say, if you cool down to be near 0 Kelvin, you wind up with a tie line that you draw, and the tie line gives you a 2-phase region. This alpha phase is almost pure component, well, whatever's over here, whatever, say, calls an AB phase diagram A, and over here, the composition is almost pure B. And as I said, this is a consequence of the laws of thermodynamics. So this is one example phase diagram. Let's look at another. So this is the phase diagram for magnesium, lead. Again, it looks a little bit complicated. I want to point a few things out. One, I want to point out that the phase diagrams give 2 axes. This one's in Celsius, this one's in Fahrenheit. You might also have Kelvin in here as well. And then the x-axis also varies. This is weight percent. the top axis is atomic percent. And, these don't line up very well at all. Like that's 60 weight percent lead. 60 weight percent lead is actually about 17 atomic percent lead because of the difference in the atomic weight between lead and magnesium. So when you're working, make sure that you are very careful with the units you pick. So looking at this phase diagram, what I want to point out is that this is actually two eutectic phase diagrams. So for example, if I put a piece of paper here, this is a eutectic phase diagram where we have some composition here and a composition here. Here's some solid solubility. Here, there's no solubility. We'll come back to that. This side is also the eutectic, right? We've got the eutectic temperature here. We got a eutectic composition, solid solubility, liquid, alpha plus liquid, alpha plus Mg2b, Mg2b plus liquid, liquid. This Mg2b, it is a stoichiometric compound. We call this a line compound. If you look up here at the atomic percent, right, that is 33%, which corresponds to Mg2b. So 2 parts magnesium to 1 part lead. This is a line compound and it's stoichiometric, so it will not form a solid solution. When you form this, you can essentially think of it as taking a phase diagram like this: liquid alpha plus liquid alpha, beta, beta, beta plus liquid, and then shrinking these until they're 0. Remember, the width of this phase region tells you the degree of solubility. As I move, say, this direction, I eventually cross a solubility limit and I start to precipitate out alpha phase. Well, if I turn this instead to a phase diagram that looks like this, this is going to be, say, some alpha phase. This is going to be some beta phase, alpha plus beta. What I'm saying is that there's 0 solubility. So if I move even a little bit into this region, I start to precipitate out a beta phase. So that's a line compound. But in general, though, these type of situations where you go through and you identify your line compounds, or you identify other solid solubilities, and I'll show you one of those in a moment, and then look at the phase diagram as a bunch of sub-phase diagrams. This is a handy way to work with it. And of course, once you have this sub-region, then any point you can say, okay, well, I'm going to pick that composition, go up, I have liquid, cool down, I've crossed the solidus, I get alpha plus liquid, keep cooling down. Here now I get alpha plus Mg2b. So we use Greek letters to specify solid solutions. Alpha is a solid solution of magnesium and lead in whatever structure the magnesium takes. This beta right here is a very thin little slice. That beta is lead with some magnesium in it. The line compounds, however, instead of specifying it as a Greek letter, because it's a stoichiometric compound, we specify it with the chemical composition. This is copper zinc. So copper zinc, again, we're starting to get even more complicated. Zoom in. So copper zinc, that's copper. This is Zn. I want to point out a few kind of interesting points here. This is weight percent zinc. This is an alpha phase. This is liquid, beta, gamma, epsilon, eta. Now, what is kind of neat about this, or what's worth pointing out, is that this is a single phase region, and this is also a single phase region, and this is a single phase region. So what these represent are windows within our composition space where we have solid solutions. And this is a solid solution, and this is a solid solution, and if you want to think of it, this allows us then to subdivide our phase diagram. And I'll show you perhaps a better example here in a little bit. Actually, I don't have one. But there are better examples of this where we have the exact atomic weight. The important thing here, though, is that anywhere you have these single-phase regions, they have to be separated by a two-phase region. So if this is alpha, that's beta, that's alpha plus beta, gamma, beta, now I have beta plus gamma. Here's liquid, so we have beta plus liquid. That's gamma, so we have gamma plus liquid. And if you are given an empty phase diagram, what you start doing is you start from the left or the right and work your way across the bottom, identifying line compounds, and then counting between single phase, two phase, single phase, two phase, single phase, two phase, single phase, two phase, single phase. And that would allow you to identify where the single phase regions are, and then that also lets you identify where you have to have two phase regions. For example, here, that's a little tiny tail there. That is a eta plus liquid. Now, there's a few other features here that are kind of unique. One of those is a different color. One of those is this little triangle. And in that little triangle, you have delta. And between, on the left side of the delta, you have gamma plus delta, because we have gamma. On the right side, you have liquid plus delta. In this little, I guess, kind of anvil-shaped region here, because you have epsilon there, delta there, that must be delta plus epsilon. Now, the interesting thing about it is that as this delta drops down, it's dropping down into a gamma plus epsilon region. So if you were to heat it up, cool it down into this delta region, as you cool down into the gamma plus epsilon, all of the delta phase must transform into a gamma plus epsilon. That is called a eutectoid. Point. So a eutectic is this liquid alpha plus liquid beta plus liquid alpha plus beta. This is a eutectic. If we replace liquid with some solid, say delta, now it becomes eutectoid. So the tic versus oid are just a Latin distinction to be made. Now, something else that's interesting are these shapes. And I'll show you up here. I'll show you these a little bit better, but you notice that this kind of cap seems to go over top of the gamma phase. This and this, these are called peritectic. Right? So whereas the eutectic looks like this, a peritectic is a situation where you flip it. So now you have something that looks like this. Alpha plus beta alpha beta. Sorry, try this again. I'm not very good with the solid solutions. So if a eutectic looks like liquid alpha plus liquid alpha, alpha plus beta, beta, beta plus liquid. And this liquid, let's make it a eutectoid, like that. Solid phase. If we turn that upside down, so now it is something like this, where we have alpha plus beta, delta, alpha, call this, alpha, beta, delta plus beta, delta plus alpha, increasing temperature. Whereas this is a peritectoid, this is a eutectoid, this is a peritectic, or peritectoid, because it's solid. Peritectoid. If there was liquid involved in this, then it would be a peritectic. And we can look at this a little bit better in this diagram. So this is a phase diagram of A atoms and B atoms. Here we have a line compound, which is basically 30 weight percent B. And these A and B are also line compounds. So this is A, that's AMBN. So this is a two-phase region. This is AMBN and B, two-phase region. Liquid, so B and liquid, two-phase. Here we've got our line compound and liquid on the other side, so we have a two-phase region. And here, A is on one side and liquid's on the other, so we have a two-phase region. So the phase counting works out. This is the peritectic. And the reason it's a peritectic is because, first off, it has liquid. If these were two solids, it'd be a peritectoid. And second, we have a two-phase region which comes down to a single-phase region here. So we get the picture I was drawing here. Two phases, and as you cool down, it goes into a single phase. Now what's, I think, is neat about a peritectic or peritectoid reaction is that there is this little window in here. And within this little window, if you pick a composition here, you cool down, you start in liquid, you go through the liquidus, so now you have liquid plus A, and then if you keep cooling down, you cross that GD line, and now you're in this region with liquid plus AM plus BN. So in the process of going through this peritectic temperature, all of the A compound has to be completely reabsorbed into the liquid, and an AMBN compound has to solidify out. So you actually have a reabsorption and solidification both simultaneously occurring as you pass through that. And I think that's something which is pretty neat and is not at all uncommon to find in phase diagrams. So this is something that you should become comfortable with. And again, when it's just a matter of, say, reading a phase transformation or reading a phase diagram, right? You're still doing the same thing. You come down, drawing a tie line, identifying the phase fraction of B by taking this divided by this, the phase fraction of liquid, that divided by that, and then the composition of B from there, and the composition of liquid from there. Cool down to this region. Now in this region, we draw a tie line. We have the phase fraction of B as that divided by that, the phase fraction of AMBN as this divided by this, and then the compositions are line compounds because if I draw my tie lines where they touch the phase boundaries and draw them straight down, I get the stoichiometric AMBN and B. Talking about this region with a peritectic, if I start in liquid, I cool down. At this point, I can talk about the phase fraction by drawing a tie line. The fraction of solid is this divided by that. The fraction of liquid is this divided by this. The composition of solid is straight down, pure A, and the composition of the liquid comes from looking where the tie line crosses the phase boundary and drawing a line down. If I continue to cool, now that I'm in the liquid plus AMBN region, I can again draw a tie line. From the tie line, I can determine the phase fraction liquid by taking this divided by this, and the phase fraction solid as this divided by this, and the composition of the solid comes from drawing this line down. The composition of the liquid comes from drawing where the tie line touches down. So the fundamentals are the same. The phase diagrams themselves may look particularly hairy, but you can work with that. It's some very simple rules. And here we can continue to cool if we wanted to. So we continue to cool this and say we cross into this now AMBN plus B. Now in this region we draw our tie line. The phase fraction of B is this divided by this. The phase fraction of AMBN is this divided by this. And the compositions, again, are stoichiometric AMBN and B.